Google, Microsoft, and Amazon are all jumping into the quantum computing game.
Jensen Huang once said it might take more than 30 years, but the timeline for commercialization is getting shorter and shorter. So why is it being called the future of computing? Let's dive in.
Hi everyone, this is Jay Lee. So what is quantum computing? Well, put simply, it's a whole new way of computing that uses the principles of quantum mechanics. It's designed to solve incredibly complex problems much faster and more efficiently than traditional computers ever could. It works by using special units of computation called qubits that harness the unique properties of quantum particles. And here's the mind-blowing part. With this approach, quantum computers could solve problems in just days or even hours that would take today's supercomputers decades or centuries to crack. To really get a grasp on this technology, we need to understand a few key principles of quantum mechanics. We'll keep it simple. First up is superposition, arguably the most fundamental concept in quantum mechanics. In classical physics, something is either in one state or another, but in quantum mechanics, a quantum particle can exist in multiple states at once. This is what we call a superposition. You could think of it hasn't decided on a definite state. That's why a quantum particle only settles into a definite state after it's observed. Until that moment, it doesn't choose one. It just stays in a mix of all possible states. One of the most famous thought experiments that explains this idea of quantum superposition is Schrödinger's cat. You've probably heard of it as the cat that's somehow both alive and dead. Here's how it goes. Imagine placing a cat inside a sealed box, along with a device containing some radioactive material and a vial of poison. Then you close the lid. Now, the radioactive material has a 50% chance of decaying within a certain time. If it does decay, the mechanism releases the poison and the cat dies. But from the outside, there's no way to know what's happening inside the box. We don't know if the radioactive material has decayed and triggered the poison, or if nothing happened at all. Until we open the box, the cat is in a state of both being alive and dead at the same time. So until we actually open the box, the cat exists in a superposition, both alive and dead at the same time. And the moment we lift that lid, the superposition breaks, and the cat's fate is decided. This idea of superposition connects directly to how quantum computing works, specifically through its basic unit of information, the qubit. In a regular or classical computer, the smallest unit of data is a bit, and a bit can only be in one of two states, either 0 or 1. All the data and calculations are built from combinations of those two numbers. On the other hand, quantum computing uses qubits, which can be both 0 and 1 at the same time. That means a quantum computer can explore multiple calculation paths all at once, giving it the potential to process information much faster than classical computers. For example, in classical computing, 2 bits can represent 1 out of 4 possible values, 0, 0, 0, 1, 10, or 11, just one of those at any given moment. On the other hand, 2 qubits can represent all 4 combinations, 0, 0, 0, 1, 10, and 11 at the same time. That's because qubits can hold both 0 and 1 simultaneously. In other words, they exist in a superposition of all those possible values at once. That's why quantum computers can handle way more information at once compared to classical ones. And this gives them a big advantage when it comes to solving complex problems. Another key phenomenon is entanglement. Entanglement means that 2 quantum particles become linked in such a way that measuring the state of one instantly affects the state of the other, no matter how far apart they are. You've probably seen this in movies inspired by quantum mechanics, where something happens in one world and instantly it affects another, as if space and time don't exist. That's the idea behind quantum entanglement. Here's another example. Imagine 2 coins that are mysteriously connected. Every time you flip them, if one shows heads, the other must show tails. And no matter how far apart they are, even on opposite sides of the universe, the moment you check one, the other's result is instantly determined. That's how quantum entanglement works. In quantum computing, this principle of entanglement is used to link multiple qubits together, making them work as one massive unified system. Because entangled qubits can instantly influence each other, they can carry out many calculations at once, allowing quantum computers to tackle complex problems much faster than traditional ones. And finally, there's quantum measurement and what's called collapse. In quantum mechanics, the moment you measure a quantum state, it collapses into a single definite outcome. That means the qubit, which was in a superposition of both 0 and 1, settles into either 0 or 1 when measured. So in the end, collapse is the step where the quantum computer wraps up its calculations and produces a final result. In quantum computing, it's important to minimize measurements, since measuring too early can disrupt the process. The key is to measure only when it really matters. That way you minimize the loss of qubits and get more accurate results. If errors start creeping into the qubits during the process, the system's computing power naturally takes a hit. That's why designing algorithms that minimize measurement is considered one of the key techniques in quantum computing. Another phenomenon is decoherence. This refers to the process where a quantum state breaks down or collapses due to interference from the outside environment. The qubit loses its quantum properties and can no longer maintain its delicate state. In this case, the external environment includes everything from temperature and electromagnetic fields to stray particles. If the quantum system isn't perfectly isolated from all of that, superposition gets disrupted and the state eventually collapses. It's kind of like trying to focus on work in a noisy room. Too much background noise and the system starts to fall apart. That's why many companies are building ultra-cold, ultra-high vacuum environments to keep decoherence to a minimum. On top of that, they're developing quantum error correction techniques that can detect and fix errors in real time, even when decoherence does happen. Now let's take a closer look at the qubit, the fundamental unit of quantum computing and the key ingredient that makes quantum operations possible. Just like how we use advanced EUV technology to pack ever smaller, more precise circuits into today's high-performance CPUs and GPUs, quantum computing also relies on incredibly precise techniques to build qubits. And understanding how these qubits are made is key to making sense of the global race in quantum tech. So let's take a look. There are 5 ways to implement qubits: superconducting, ion traps, topological, silicon, and photonic. This order also considers the development and commercialization potential of qubit technology. Let's go through them in order. First, superconducting qubits are based on the phenomenon where electrical resistance drops to zero at extremely low temperatures. The qubits are created by layering a superconducting material onto a silicon substrate, then forming circuits. The quantum state of the current flowing through these circuits is what functions as the qubit. Because it builds on existing silicon semiconductor platforms, this method offers high scalability compared to other approaches. It's relatively easier to increase the number of qubits and control them. That's why companies like IBM, Google, and Rigetti Computing are leading the quantum race using this superconducting qubit technology. But creating a superconducting state isn't easy. Since it only appears near absolute zero, around minus 460 degrees Fahrenheit, it requires expensive and complex cooling systems to maintain those conditions. On the flip side, if that environment isn't perfectly maintained, superconducting qubits are especially prone to decoherence. Their superposition state can collapse much more quickly compared to other types. Next is the trapped ions, another widely used approach. It works by using electromagnetic fields to trap ions in place, then using their energy levels as qubits. Sounds complicated, right? Here's a simpler way to picture it. Think of a net made of electromagnetic fields holding tiny ion particles like little floating balls in place. Then lasers are used to move and manipulate them, creating quantum superposition. Since this method uses naturally occurring ion atoms, it's very stable and allows for highly accurate quantum operations. And because the ions are carefully held and controlled in isolation, they interact less with the outside environment, meaning they can maintain their quantum superposition for longer periods. On the downside, trapping and controlling ions is technically very challenging, so it's harder to scale up the number of qubits compared to the superconducting approach. Plus, the system has to be kept in an ultra-high vacuum, which makes it expensive to build and maintain. Companies like IonQ and Alpine Quantum Technologies are leading the way with this ion trap method. Yeah, that's a tricky one too. So let's try a simple comparison. Imagine the Majorana particle as a special kind of string, one that's almost like a pair of identical twins joined together with no clear beginning or end. Now think of tying knots in that string. If you tie it one way, it represents a 0. Tie it a different way, and it represents a 1. The information is stored in the shape of the knot itself. That's the basic idea behind topological qubits. Yeah, that's a tricky one too. So let's try a simple comparison. Imagine the Majorana particle as a special kind of string, one that's almost like a pair of identical twins joined together, with no clear beginning or end. Now think of tying knots in that string. If you tie it one way, it represents a 0. Tie it a different way, and it represents a 1. The information is stored in the shape of the knot itself. That's the basic idea behind topological qubits. But here's the cool part. No matter how much you shake the string, the shape of the knot doesn't change easily. That's because the information isn't stored in where the knot asterisk is asterisk, but in asterisk how asterisk it's tied. So even if there's noise or interference, the knot, and the data it holds, stays stable. In other words, information stored this way is much less likely to break down or get lost. So in the end, topological qubits work by using Majorana particles to store information in a stable, knot-like form. And thanks to that, quantum computers built with topological qubits are expected to be much more resistant to external noise, making them far more stable overall. That also means error rates are extremely low. But like any technology, it comes with challenges. For one, Majorana particles don't occur naturally. They have to be artificially created and precisely controlled, and that requires highly advanced technology. Right now, this approach is still in its early stages. Microsoft is one of the big tech players betting on this method. In February 2025, they unveiled Majorana 1, the world's first topological quantum chip. The fourth technology is the silicon qubit. Just as the name suggests, it uses silicon, the same material used in traditional semiconductor manufacturing. The process involves creating quantum dots on a silicon chip, then using the spin of an electron inside those dots to form a qubit. One big advantage is that silicon qubits are highly compatible with existing semiconductor technology, making large-scale production more feasible. But on the downside, they're relatively sensitive to external noise, which makes it harder to maintain and control their quantum state for long periods. Intel is actively investing in quantum computing based on this silicon qubit approach. And finally, we have photonic qubits. This method uses particles of light, photons, to represent qubits. It takes advantage of a property called polarization, which is the direction in which the light wave vibrates. For example, vertically polarized light can represent a 0, while horizontally polarized light represents a 1. Because it uses light, this method allows information to travel long distances and even works at room temperature. That's a big plus. But photons are hard to trap, and even harder to control. Think of it like trying to catch sunlight with your hands. It's the same idea. One challenge with photons is that they don't interact easily with each other, which makes entanglement between qubits much harder to achieve. That's why building a full-scale quantum computer with photonic qubits is especially tricky. Still, many companies, both in Korea and around the world, are actively exploring this approach. So we've just gone over the 5 main types of qubit technologies. If we sum it all up in a table, it would look something like this, listed in the order of current technological maturity. Keeping this in mind will definitely help you better understand where the quantum computing industry is headed. Now the big question, just how fast are these quantum computers? To start with, in theory, a quantum computer with asterisk and asterisk qubits can be up to seconds and times faster than a classical computer using bits. For example, 1 qubit is twice as fast as 1 bit, 2 qubits are 4 times faster, and 4 qubits. That's a 16-fold increase. This exponential growth is what gives quantum computing its incredible speed advantage over traditional computing. That's why Google's 53-qubit quantum computer, Sycamore, made headlines in 2019. It solved a problem in just 200 seconds, a task that would have taken the world's most powerful supercomputer at the time around 10,000 years to complete. But quantum computing isn't faster at everything. At least not yet. It shows the biggest advantage in specific types of problems where quantum algorithms can be applied. 2 of the most well-known are Shor's algorithm asterisk and Grover's algorithm asterisk. Shor's algorithm uses quantum superposition and entanglement to perform prime factorization much faster than classical methods. It can also be applied to molecular energy calculations and simulations in chemistry. Grover's algorithm is known for its ability to search through unstructured databases much faster than classical methods. This opens up possibilities in areas like drug discovery and genetic analysis. It's also well suited for optimization problems, like logistics planning or financial portfolio optimization, where you need to explore countless combinations and zero in on the best one. And since it's great at quickly finding the right data from large sets, Grover's algorithm can also help speed up machine learning by accelerating how fast AI models learn from data. So ultimately, quantum computing isn't just about speed. It has the potential to accelerate progress in fields like medicine, materials science, and AI by handling complex problems much faster than before. Now, let's wrap up by taking a closer look at the current state of the quantum computing race. We've already mentioned a few key players while going over the core principles, but now it's time to dig a little deeper and see who's doing what in this rapidly evolving field. Leading the charge are Google, Microsoft, and Amazon, 3 giants already dominating the cloud market. In late 2024 and early 2025, all 3 unveiled new quantum chips, ramping up the competition. Google introduced Willow, a 105-qubit chip. Microsoft revealed Majorana 1, an 8-qubit topological chip. And Amazon joined the race with Ocelot, a 9-qubit chip. Another key player that often flies under the radar is IBM, a longtime leader that's been steadily pushing quantum technology forward. True to its legacy as the company that helped define the PC era, IBM is now leading the way in quantum computing as well. It's been researching quantum tech since the 1990s, and starting with the 27-qubit Falcon chip in 2019, IBM has steadily pushed forward, unveiling the 121-qubit Condor chip in 2023, with plans to go beyond 4,000 qubits in the coming years. So how do the strategies of these 4 companies differ? Starting with IBM and Google, they both use asterisk superconducting qubits asterisk, which, as mentioned earlier, have the advantage of being relatively easy to scale. IBM has already passed the 1,000 qubit mark, while Google has nearly doubled its qubit count, from 53 in its first-generation Sycamore chip to 105 in the newer Willow chip. But there's a key difference between IBM and Google. IBM's strategy is to keep scaling up the number of qubits to maintain a technological edge, even if that means a slight drop in accuracy. The idea is that sheer volume can help offset the imperfections. Google, on the other hand, is focusing more on reducing quantum errors rather than rapidly increasing qubit count. Their goal is to improve reliability before scaling up. Quantum error refers to calculation mistakes caused by the instability of qubits. Experts estimate that current quantum computers have an error rate between 0.1% and 1%. Now, if we assume a 1% error rate, running the same operation just 100 times could drop the accuracy to around 36%. That's why many experts have argued that overcoming quantum error would be one of the biggest hurdles, but Google seems to have made a breakthrough with its Willow chip by introducing something called a logical qubit. Instead of performing a calculation with a single physical qubit, this method uses a group of qubits working together as one logical unit. By using multiple qubits together, the system can detect and correct quantum errors as they happen during computation. It's a way of overcoming errors while the calculation is still running. Microsoft is the only major player using topological qubits. As mentioned earlier, topological qubits offer higher stability compared to superconducting or ion trap qubits, which helps reduce error rates. That's why Microsoft claims it can achieve strong computational performance with just 8 qubits. Amazon, the most recent to reveal a quantum chip, is using its own approach called the cat qubit. Cat qubits are a special type of qubit designed to stably maintain both 0 and 1 in superposition. Traditional qubits also hold 0 and 1 simultaneously, but they are highly sensitive. Small changes in the environment can easily trigger errors. This constant switching between 0 and 1 inside a qubit is known as a bit flip error. Traditional qubits are quite vulnerable to it, but cat qubits are much better at suppressing these errors on their own. It's like placing an item on a shelf. Regular qubits tend to have that item flip between the upper and lower shelves unpredictably. With cat qubits, the item stays where you put it, holding its position much more reliably. Thanks to this, Amazon claims cat qubits can reduce errors by up to 90%, allowing for highly accurate computations even with fewer qubits. As we've seen, each company is approaching quantum computing with different principles, each with its own strengths and challenges. Right now, IBM and Google are clearly leading the pack, while other players like Microsoft and Amazon are steadily catching up. And who knows, more big tech names might jump into the race sur billeux. Today we took a quick tour through the key technologies behind quantum computing and the fundamental principles of quantum mechanics that make it all possible. As you've seen, not all quantum computers are built the same. Different approaches use different principles, and each company has its own unique strategy. Of course, there's still so much more to talk about when it comes to quantum computing, and we'll be diving deeper bit by bit in future episodes. That's all for today. If you enjoyed this video, don't forget to like and subscribe. Thanks for watching.